Hi everyone. All right, in this video I want to go over multinomial experiments. And let's see what are multinomial experiments. It's chi-squared test for goodness of fit and the other one chi-squared test for independence or homogeneity of proportions. Now this I covered in the last video, and test of independence are just the contingency tables. Here we're going to go over chi-square test for goodness of fit. So let's see what that is first. Chi-square goodness of fit test. The goodness of fit test determines if a particular claim about a set of proportion fits a specific distribution. In other words, a set of expected probabilities support corresponding observed frequencies. Now we'll see what this is with a couple of examples, and you'll see it's not that hard. The test uses right-tailed chi-square distribution. Please remember that. Whenever we deal with multinomial experiments, it's always chi-squared right-tailed test with the significance level, of course. The test uses a chi-square test statistics. So if it's chi-square distribution, of course, the test statistics will be a chi-square value. The degrees of freedom in the number of categories minus one. Again, be patient. We'll see an example. Now here are examples of null hypothesis goodness of fit test. For example, we can check to see if a die is fair. What is a fair die when the probability of all the numbers are the same and it's 1/6? So HO, you write P1 equals to P2 equals to P3 equals to P4, P5, P6, and that equals to 1/6. The probability of a car accident during the week is uniform. So uniform, that means P Monday, P Tuesday, P Wednesday, and so on equals to 1/7. And don't forget, this is always for HO, H1, we're going to talk about that. The distribution of rent throughout a month is uniform. P of January equals to P of February and so on, up to P of December is 1/12. So in these three cases, all the probabilities of this are the same. However, we can have this last example. In an auto center, the probability of selling black car is 40%. The probability of selling a silver car is 30%. The probability of selling a white car is 10%. The probability of selling a yellow car is 10%. And the probability of selling the other colors is 10%. So to write here, the probabilities are not the same, but when you write HO, you just put one by one. P of black car is 40%, so it's 0.4. P of silver car is 30%, so it's 0.3. P of white car is 10%, which is 0.1. And P of yellow car and other colors is 10%. So that's how you write the HO, or the null hypothesis. Now let's go over the rules. Rules of goodness of fit test. A goodness of fit test, the original claim, the null hypothesis always represents the expected probabilities. So the alternative hypothesis is always represented by the statement at least one is different. Remember this too. So no numbers in HA or H1. You just write the sentence at least one is different. The data collected to examine the validity of the expected probabilities, the null hypothesis, is called observed frequencies, or we call them O's. So O stands for observed. Expected frequencies are obtained by the product of the individual probabilities in a null hypothesis with the total number of observed frequencies. So the expected value, basically, that's what you do for E1. E stands for expected. You take P1 times the sum of the observed frequencies, and so on. The sum of observed and expected frequencies must always be the same. The rejection region is the test found using the right tail chi-square distribution. We talked about that with k minus 1 degrees of freedom and alpha significance level. Note k represents the number of categories. For example, when you roll a die, you have 6 numbers and you have 6 categories. So the degrees of freedom is going to be 6 minus 1, which is 5. The test statistics is given by this formula, just like we saw with contingency tables. So chi squared equals to sum of O minus E squared divided by E. And if you expand that without, write it without the summation notation, that's how it is. O1 minus E1 squared divided by E1 plus O2 minus E2 squared divided by E2, and so on. So let's see some examples here. Again, let me just go directly to the example. A die is rolled 120 times and the following outcomes were observed. Let's understand the table. We roll a die 120 times and we count the number of times 1 is shown, and that's 17. 2 is 25, 3 is 17, 4 is 23, and so on. Of course, if you add all these numbers, you're going to get 120 times. Now, the question is, test the belief that it's a fair die at 0.01 significance level. Now, what is a fair die? We know a fair die, a die is fair when the probability of each number is the same and it's 1/6. So you write HO equals to P1 equals to P3 equals to P4 and so on, and that equals to 1/6. H1 is going to be at least one is different just for all of them. That's how you write, or alloyed, which stands the same thing. So step 2, we need to use O's and calculate E's. Recall that O's come from the data or the table, observed frequencies, and E's are calculated by multiplying each individual expected value found in HO by the sum of the observed frequencies. So these are O's. I put it here for you. You add all the O's or observed values, you get 120. And if you want to find the expected value for E1, for example, here you take P1 times the sum of, which is 1/6 times 120. And let's think about it. When I roll a die, excuse me, 120 times, I expect to see the number of times that 1 comes is 20. And that goes for all the numbers because the probability is 1/6. It's not going to happen all the time, but that's what it's expected. So the expected values for all of them is going to be 20. And we said the sum, if you add those two, you have to get the same thing. You can make a table and calculate the test statistics. So you can do O minus C squared divided by E. So it's going to be 17 minus 20 squared divided by 20 is going to give you 0.45. And so on for each of them. Let's do one more. 25 minus 20 divided by 20, which is the expected value, is going to give you 1.25. If you calculate all those, then you're going to get 4.3. Now, step 3, of course, we have to find the critical value. So, we said, recall that the rejection region for multinomial experiments is going to be right tail or right tail chi distribution. This example, the number of degrees of freedom is k minus 1, and we said we have 6 categories because we have 6 numbers. 6 minus 1 is 5, and alpha was given in the problem to be 0.05. So go to your table, the chi-square table, and I did that for you. If you go 0.05 degrees of freedom 5, you get 11.01. So now let's see what happens in summary here. Or in short, P1 equals to P2. So you write that equals to 1 over 6. At least one is different for H1. We found the test statistics to be 4.3 is right here. And the critical value is 11.07 from the table, chi-square table. The test statistics is in non-shaded region. And non-shaded region, the first conclusion is going to be failed to reject HO. When we fail to reject HO, we accept HO, or we have enough evidence to accept that all the probabilities are the same and the die is fair. So the probabilities are distributed as expected. So we can say we have enough evidence to support the claim that the die is a fair die. Now, a calculator, I put the steps. You go to stat, number 2, edit. Put all the O's in L1 and E's in L2. Then go to stat again, go to test, and scroll down to D and find chi-square GOF, which stands goodness of fit test. So what you're going to see on the screen, the observed values in L1, expected values in L2, and then you just push calculate or enter calculate, and you get chi-square is 4.3, which is the test statistics. So you don't need to do the hand calculation, although it's good to do it 2 or 3 times just to get used to that. And of course, the calculator is going to give you the p-value and the degrees of freedom. I would like to do this. Let me share my calculator and show you how the calculator works for this problem. So, okay, if we go, the first thing you want to do, go to stat, and then again, edit, enter that. Then you have L1 and L2. You put the observed values in L1. I already did that for you. 1725, 1723, 1523, and all the expected values were 20. So L1 observed values, L2 expected values. Once you enter all those, then you go to stat again, then you go to test, then you scroll down to D, and these chi-square GOF test, goodness of fit test. Enter that. It's all done already since you entered the values, observed values in L1, expected in L2. Of course, degrees of freedom is 5, and you just say enter. And the calculator will give you the test statistics. And of course, the p-value. Here, the p-value is much larger than alpha, and that's another way to make the conclusion, which is going to be failed to reject HO. All right, we can probably do another example that's a little bit different. So example 2. Let's go over this. It's believed that the proportion of people with A, B, O, and AB blood types in the population are respectively 0.3, 0.2, 0.4, and 0.1. What does that mean? So A type is 30%, and B type is 20%. O type is 0.4 or 40%, and AB is 0.1 or 10%. When 400 randomly picked people were examined, the observed keyword, observed numbers of each type were 118. That means 118 for A. These are the frequencies. 86 for B, 136 for O, and 60 for AB. At the point of our significance level, test the claim that the frequencies are distributed as believed. So we picked the sample, we counted the blood types, and that's the answer. Let's see if that matches with what is expected. So in this case, step one, if you write HO, they're not the same. So we write it anyway. The probability of A type is 0.3 or 30%, B type is 0.2, O type is 0.4, and AB is 0.1. So that's our HO. H1 again, always the same. At least one is different. So step two, now we have the observed values from those 400 people. O1 is, which is OA, we can say is 118, O2 is 86. So here in the problem, O3 is 136. So that's for O type, and O4, which is type AB, is 60. Let's calculate the expected values. We said we take E1 or EA is going to be P1 times the sum of the observed frequencies. So it's going to be 30% of, that's what we accept to have. 30% of 400, which is 0.3 times 400. E2 or EB is 20% of 400, which is 0.2 times 400 is 80. E3 is 0.4 times 400, which is 160 or 40% of 400. And finally, E4, which is again the same thing as EAB, is PAB times the sum of the observed values or 400, which is 40. So that's pretty easy to calculate. Now the rejection region, we have 1, 2, 3, 4 categories. So we know the degrees of freedom is going to be 4 minus 1, which is 3, and 0.05. So if you go to the table, chi-square table, 0.05, degrees of freedom 3, you get that critical value. So which is right here. And we know this is alpha. Now, let's calculate the test statistics. So again, the observed values, you can put that in L1. The expected one, you can put that in L2. And you can do this one by one. I already did that for you. And if you do O minus E squared divided by E, and you add them, you get 14.08. So this is our test statistics. Calculator, I put the commands for you. You go stat edit. Again, O's in L1 and E's in L2. Then you go to stat, test, scroll down to, as I showed you with the last problem, scroll down to D chi-square GOF test. That's what you're going to see on the screen. Just go to calculate and enter, and you will see the same value. So calculator will do that for you. Let's see the conclusion. So we said this was our HO, and in H1, we said at least one is different. And critical value 7.815, and this is the test statistics. So this is our critical value, and this one is the test statistics. And again, they're both chi-squared values. So as we noticed, the test statistics now is in the shaded region. So we're going to say reject HO. Reject HO, then you can come and put reject here and accept H1. So we are accepting that at least one is different. So reject HO, the probabilities are not distributed as expected. At least one is different, and I wrote that for you. And that's it. I think for goodness of fit test, it's pretty straightforward and easy. Please watch this video 2 or 3 times, and you can then start solving more problems. Thank you, and I'll see you all in the next video. Have a great one, everyone.